So at the end of class last time, I said that we were going to take a look at a graph of a transformation and identify what transformation has taken place here. So if you're given a graph that looks like this, one thing that might help you to do is label some ordered pairs on it. So we got -3, 5, -2, 3, 1, 1, and 6, -1. And our job is to figure out what graph has been transformed here. Now, it's pretty clear which graph has been transformed. I'm sorry, the more difficult thing is to be able to figure out the equation that generated this transformed graph. So what's our parent function here, everyone that wants to play? Parent function, which one of our 5 basic functions got transformed? F of x equals the square root of x. We know that because we know what all of our basic functions look like. We know what absolute value looks like. We know what cube root looks like. We know what square root looks like, and this is a square root graph. The idea is to figure out how to write the equation that gave us this right here, gave us this picture. So let's talk about what's happened. First of all, the original function looks like this. So since it now has this shape, one of the things that happens was it was reflected over the x-axis. Since it's now flipped over, we can see the way it's flipped over, we can see that at some point there was a reflection over the x-axis. Does it also look like it's been shifted? Yeah, to figure out how it's been shifted, the secret basically is to kind of look at what's happened maybe to this point right here, this 0, 0 point. So at one point, this looks like this graph has been shifted maybe 3 units to the left. And it's been shifted 5 units up. And I wanted to talk about this next one because this one's the hardest one to see when you're looking at a graph, and that is this graph has been vertically stretched. And the way I can tell this graph has been vertically stretched is by thinking about the first 2 points we kind of think of when we think of the square root graph. When we think about the square root graph, the 2 easiest points to think about are the 0, 0 point and the 1, 1 point. And those have a vertical distance between them of 1 unit. Everyone with me on that so far? But if you look at this one, those 2 points have a distance between them of 2 units after the transformation took place. So therefore, we have a vertical stretch by a factor of 2. So now the idea is we have to put all those ideas together and come up with the equation. This is probably the trickiest type of problem to do in this section, going the backwards from the pictures, and there's not a lot of them, but you will see one in your homework if you haven't done it already. So let's see what we need here. We'll call this thing g of x. Make a nice big function here, drop an x in there, and figure out where I need everything. Let's worry about those shiftings first. We shifted up 5 units. That's the quick one. We shifted 3 units left. So do we need a +3 or a -3 on the inside?
Plus.
Be a +3. That's the backwards one. That's the backwards one. So we need a +3. We need a 2 in front of the whole thing. We need a 2 in front of the whole thing for our vertical stretch. And what's the last thing I need to figure out? The reflection. Where does that minus sign go, on the inside or the outside? Well, when you reflect over the x-axis, even though you're reflecting over the x-axis, that does change the y values. And if you're changing the y values, does the minus sign go on the inside or the outside? Outside. And that's it. And I'm not saying you have to do dozens of these in the homework, but I am saying that you will have to see one of these in the homework, because I did it in the homework, and so it is good to have this here as an example. because it is kind of tricky to figure these out. Last idea in 2.7 is to go back to even and odd functions. All right. Copy. So we've seen this picture before. This is just a picture I made that show a bunch of different even functions. Besides just these three even functions here, which are just kind of random functions, we also know that f of x equals x squared and g of x equals the absolute value of x are even functions. And that means they are symmetric about the y-axis. Even functions, all even functions, not just these two basic functions, but all even functions are symmetric about the y-axis. That's what makes them even. And there's a couple observations we can make about even functions. One is this. If you reflect an even function over the y-axis, and that is your only transformation, the graph will not change. Even functions have the characteristic that if you reflect them over the y-axis, then they will not change at all because they're already symmetric about the y-axis. So you will see no difference when you do that. What that basically means, everyone, is that putting the minus sign right up next to the x does not change the function at all. Let me show you what I mean. F of x equals x squared is the same as that. And the parentheses are important, otherwise I'm doing the other kind of reflection. The parentheses are important there, everyone. So don't forget those parentheses. But this is the same thing as this, because that's a reflection over the y-axis, it doesn't change. Same thing with the absolute value. It does not make a difference if you put a negative up against the x. Make sure the negative is on the inside. Another way to summarize that, and this gets a little bit wordy, but I'll do my best so it's clear to you, is this. Inserting two numbers of the same magnitude, I'll talk about that more in a second, but different sign into an even function yields the same y value. Now I'll explain to you what that means, because that's a little bit wordy. Inserting two numbers of the same magnitude but different sign into an even function yields the same y value. What does that mean? It means this. If h of x is even, and we know that h of negative 3 equals 5, then h of 3 equals 5 also. In other words, if you put in like negative 3 and 3, you'll get the same answer. If you put in negative 12 and 12, you'll get the same answer. You put in 10 and negative 10, you'll get the same answer. Because the negative sign doesn't make a difference as to what you get for an answer. And if you don't believe me, just think about the absolute function of the squaring function. it doesn't matter when you square a number if it's positive or negative. If you square 3 or negative 3, you get the same answer. Does everyone agree with that? If you take the absolute value of 12 or negative 12, you get the same answer. And that's actually going to help us understand even functions even more and more. So that's how an even function works. All right, let's review odd functions. So I'm going to bring up another picture that we've had in the past, but talk about it again. Odd function. Okay. Oops. Odd functions are symmetric about the origin. F of x equals x cubed, and g of x equals the cube root of x are odd. So in addition to these odd pictures up here, these two that I drew up here, two other odd functions are x cubed and the cube root of x. Cube root of x is the one that in some pictures looks like it's failing the vertical line test, but it doesn't. What does it mean to be an odd function besides just saying it's symmetric about the origin? This is what it means. If the only transformation you do is a reflection, then a reflection over the y-axis or x-axis has the exact same result. So the even function did not change at all when we reflected it over the y-axis. With an odd function, it will change if you reflect it, but the idea is this. If you reflect over the y-axis or the x-axis, you will get the exact same answer you got before. And you can actually see, I'm sorry, not the exact same answer you had before, but the same answer for both those types of reflections. So let me just show you an example of what I mean by that. Here's f of x equals x cubed. If you go ahead and put a negative in front of the whole thing, that should do a reflection over the x-axis. So what that will do is it will swing this piece down here and swing this piece up here, because we are going around like that. So the whole thing goes like this. But if you did it over the y-axis and spun around this way, then this piece swings over here, this piece swings over here, and you get that. So an odd function will change when you do a reflection, but it will change the same way for either type of reflection. Furthermore, for any odd function, if you change the sign on the x value you input into the function, you also change the sign on the y value. So if we have an odd function, and we know that when you plug in a -3, you get a 4, if we know that whatever this odd function is, if you plug in a -3, you get a 4, then we know that if you plug in +3, you get -4. So the way an odd function works is both reflections do the same thing. And the other way it works is if you change the sign on your input, in other words, if you were change your negative number you were putting into a positive, or you change your positive to a negative, that will also change the sign on the y value. Here's another one, just so you're clear. If h of 2 equals 19, then h of negative 2 gives you negative 19. You change the sign on x, you change the sign on y. And that's how odd functions work. Little summary here. If f of x is even and has ab, it also has negative ab. If g of x is odd and has AB, it also has negative A, negative B. And we need to know that if we're going to work with these things. Because while two of our basic functions, x squared and absolute value of x, are even, and two of our basic functions are odd, x cubed and the cube root of x, there are an infinite number of even functions and an infinite number of odd functions. So the question becomes this, everyone. Without a graph of a function, just an equation, how can we tell if the function is even like x squared or absolute value of x, those are two even functions, or odd, like x cubed or the cube root of x, or neither? Do we know an example of a function that's neither, even or odd?
X squared.
Not x squared, but
Cube.
not that one.
Square root.
Square root. That's okay. So much math in the morning. Yes, square root of x. All right. Here's what you do, everyone. Here's the big trick. Without a graph of a function, how can we tell if a function is even, odd, or neither? Here's how you do it. Plug negative x in for every x and simplify. That's the secret, everyone. That's the secret. If you want to know if a function's even, odd, or neither, you change every x in the equation to a negative x and you simplify. And here's the secret to simplifying. Negative x to an even power kills the negative. If you change an x to a negative x and it has an even power on it, it just kills the negative. So, negative x squared is the same thing as x squared. Negative x to the fourth is x to the fourth. Negative x to the 100th power is x to the 100th power. If you change an x to a negative x and it has an even power on it, then the negative just goes away. Because you're multiplying it by itself an even number of times, and the negatives will all cancel each other out. Negative times a negative is a positive. We've known that for a long time. Here's the other trick for simplifying. Negative x to an odd power kills all but one negative, and it is placed in front without the parentheses. So when you change all of your x's to negative x's, if it has an odd power on it, then you just get rid of the parentheses and you put the extra negative sign in front. Because when you multiply all these together, there's one negative left over. Does everyone agree with that? Because it's an odd power, so you'll have one negative left over. So no matter how big the power is, if it's an odd power, you just rewrite it like that. And if it's part of an equation, for instance, like if you have something like, 17 minus negative x to the fifth like this would simplify to 17 minus negative x to the fifth, or 17 plus x to the fifth, like that. So, what do you do to see if a function's even, odd, or neither? You plug a negative x in for everywhere you see an x, and you simplify. And these are the secrets to simplifying. This is how you simplify with an even power, and this is how you simplify with an odd power. And then you look at the new function you have, and here's what you do. If your function, after you plug in negative x and simplify, looks just like the original. And what does just like the original mean? Well, it means that after you plug in negative x and simplify, you get back to where you started. Nothing's changed. The function is even. If your function, after you plug in the negative x and you simplify, looks just like the original, it looks exactly as it did when you started, then you can say the function's even. That's pretty slick. If your function, this one's a little bit trickier, but we'll do it. After you plug in negative x and simplify, looks as though you just multiplied the original by negative 1, the function is odd. I know that one's a little bit trickier, everyone. We'll see an example of that. But if after you plug in the negative x and simplify, and you're looking at your new function, and it looks like someone just took the original function and multiplied every term by negative 1, or multiplied the entire function by negative 1, that's how you know it's odd. If it looks like someone just swept through with a negative sign. And if neither of those things happen, it's neither. It's either even or odd. And of course, we're going to look at some examples of this, everyone, because I know this is tricky when you just see a bunch of words up there and you're like, what is he even talking about? But this is how we tell if a function's even, odd, or neither. You change every x to a negative x. You simplify. And then you examine the result. And we're going to do that right now with a couple straightforward functions. About as straightforward as I can make them for this example. Okay, here are three functions, everyone. And without drawing them, we will determine whether or not they are even, odd, or neither. Those are the three options. And regardless of what you think it might be, you don't need to think ahead what you think it is. You just do the same thing to do your test. You plug in a negative x everywhere you see an x. That's the test you do for even, odd, or neither. It's the same thing. And everywhere that you see an x in the equation, you change it to a negative x inside parentheses. Parentheses we're going to get rid of very shortly, but you still need to start with the parentheses. So every x in the equation becomes a negative x. And then we use our rules for simplifying. If the negative x is to an even power, does it kill the negative completely? Yes, it does. So this one just simplifies to x to the fourth plus 6.
But you get rid of the parentheses.
I'm sorry?
Parentheses go away.
Yeah, parentheses go away, yes. That's what we mean by simplifying. We're killing the parentheses, and we're either getting rid of the negative sign entirely, or we're maybe keeping one left over negative sign. For instance, over here, negative x cubed does not get rid of all the negatives. Does everyone agree with that? There's one left over, but it can go in there without the parentheses. So this one can look like this. Negative x cubed. And then what's minus negative x going to simplify to? Plus x. Good. This last one is going to become negative x cubed plus 6. So it's really, really helpful to know those tricks for getting rid of the negative signs with the even powers and the odd powers. That's your trick to simplifying. If you don't know how to do that, then simplifying is going to be a nightmare. Now you look at these. This first one here. What do you notice? Is it exactly the same? Nothing changed. That means it's even. And what do we mean by even? We mean that when you plugged in a negative x for x, you got back to where you started. Nothing was different when you were all done. That means that's an even function. This one's trickier. But what I want you to observe on this g of x one is our result is different. But it looks like someone just took the original and multiplied everything through by a negative 1. Does everyone see that? Looks like someone just took this x cubed minus x and said, I'm going to hit that with a negative 1, and I'm going to hit that with a negative 1. So, this is odd, since when we put in a negative x, it had the exact same impact as though someone had just distributed a negative 1 to the entire function. This last one, is it exactly the same? No. Does it look like someone hit everything with a negative 1? No. So for this one, because h of negative x does not equal h of x, and because h of negative x does not equal negative 1 times h of x, it's neither. Make them up all the time. Some are even, some are odd, some are neither. It can be surprising, though, to some students which functions end up being even, and which functions end up being odd, and which functions end up being neither. And there are little shortcuts to this that people use, but sometimes those shortcuts can get you in a little bit of trouble. So I want to show you some trickier examples, as long as everyone is cool with these. Some people look at this thing and they say, look at all those odd numbers in there, that negative 3, that negative 7, the 11. But it turns out, even though these numbers are odd, this is an even function. And it's an even function because if you plug in the negative x, those even powers kill those negative signs, and we get back to where we started. So that's an even function. Don't let those odd numbers mess with your head, like the negative 3, the negative 7, the 11. This is still an even function. Yeah, question? So if you want to write one that's neither, it's pretty quick. You just do this. X to the 10th plus x to the 9th. It's neither, because one of those will change and one of them won't. So this is neither, because if you change the x's both to negative x's, then the even power will kill its negative sign, the odd power will not. And what we have is we have one thing changed and one thing didn't. And so that one's neither. Constants go with even functions. What do I mean by that? I mean that some people might look at this function right here and see all those odd powers, x to the 7th, x to the 5th, x to the 3rd, and x. And they might say, I bet this is going to be odd. Because when I put that in there, all those odd powers are all going to have one negative sign left over, and it's going to look like someone multiplied the entire function by -1. Oops, sorry. But it doesn't look like someone multiplied the entire function by -1 because the constant didn't change. Everyone see that? And that messes people bad. They're like, oh, look at all those odd powers. I bet this is going to be odd because I'm going to have one negative left over on each one of these. But nope. This right here makes the function neither. Now, just so you know, well, I don't want to call this one h of x also. I'll call this one capital H of x. Slightly different function. If it doesn't have the -7, do you think it's now odd? Do you think that's odd now, without the -7? Yeah, because if you put the negative x in now, everything will look like it's multiplied by -1. So this one is odd. Because everything did change except for that -7 at the end in the other one, so this one's odd. But it wasn't odd before. Yeah, for those of you who are unclear, I've added something to the notes, so an even function may have a constant, an odd one can't, but just because there is a constant doesn't make it even. All right, try this one. We do this. Ooh, let's switch pages. Some people look at this function and they immediately assume it's neither. And they assume it's neither because they see the square root in it. And the original basic square root function was neither. However, if you go through the proper process and you plug a negative x in here, that squared will kill that. The function does not change. That means you should not necessarily rely on little tricks like thinking, oh, because there's a square root, it must be neither. You should rely on the main method for seeing if a function's even, odd, or neither. That is, change every x to a negative x and simplify. Since this one, when we changed x to negative x, we got right back to where we started. This is, in fact, an even function. It looks quite a bit different than the original square root graph. It actually kind of sprouts off to both sides, not just one, because it's got the squared in it, and that impacts the domain. Here's the last really tricky one. What we see here is we see a function that has both even and odd powers in it. So the gut reaction might be this one is neither, because you see both even and odd powers. Is everyone hip to that, why you might think that? But here's what happens. If you change every x to a negative x, like this, then you'll get negative x cubed minus x over x squared plus 4. Now, if someone were to take the original function, g of x, and multiply it by -1, when you multiply a fraction by -1, remember what -1 looks like when you turn it into a fraction. It turns into -1 over +1, not -1 over -1. -1 over 1 is the same as -1. So when I multiply the top by -1, I get negative x cubed minus x. I multiply the bottom by 1, I get x squared plus 4. which matches exactly what I got when I plugged in the negative x. Which means this function, plugging in negative x, was the same thing as multiplying the entire function by negative 1. Which means even though you see that mixture of even and odd powers in there, this one's actually odd. Because what's the rule for odd? The rule for odd is simply this. Plugging in a negative x for every x has the exact same impact as though you multiply the entire function by negative 1. And the way you multiply the entire fraction by negative 1 is you multiply the top by negative 1 and the bottom by 1, because that's the number negative 1. This is why you want to know the technique, not just rely on shortcuts. Because the first time I saw a function like this, I thought I was all hip. I was like, oh, even powers kill negatives, odds leave it alone. This one has some even and some odd, so therefore this one's going to be neither. But it turns out I was wrong. All right. So 2.7 is done because we did the even and odd functions, and that was the big thing I didn't get to last class. So now you should be able to do your build understanding homework for section 2.7. And now we'll move on to section 2.8. And we'll do a little bit of this before we take a break. Section 2.8, as you know from doing your pre-work, has two major ideas in it: combinations and compositions. And I know from getting a lot of emails from a lot of you, the notation for compositions messed with a lot of people's heads, because they saw a little hollow circle and wondered what that was supposed to be about. Well, we'll talk about that. What you are doing when you do a combination or composition is you are going to smash together two or more functions, usually in this class just two though, to create a new function. And there are basically 5 ways to smash two functions together in this section. You might add them, you might subtract, you might multiply, or you might divide. And these are all called combinations. No matter which one of those you do, it's called a combination. The other thing we might do is plug one function into another function everywhere you see an x. And this is called a composition. Now, what the pre-work should have helped you practice was doing this with numbers. So I'm just going to briefly recap that. When you are given two functions, sorry about that. When you are given two functions, and we'll make them nice and simple, we'll just do x squared and x minus 3. Sometimes the only thing you have to do is do a combination or a composition with a number. For instance, if someone says f plus g of 4, what you do is you plug 4 into each function and add the results. And dot, dot, dot. If someone gives you f minus g, you subtract the g result from the f result. I had to make that a little bit wordy because, as we know, subtraction is not commutative, which means f minus g is different than g minus f. So depending on which one you have. If if the two letters are just jammed up against each other like that with nothing in between, that does mean multiply. So then we would multiply the results. And if one's written on top of the other, we would divide the F result by the G result. And if all I want you to do is with a number, then that's what it is really. It's just plugging the same number into two different functions and then doing something with your two results. So it's not really a trickier problem than problems you've done in the past, it's just a slightly longer problem. There's an extra step at the end. Now that you've got this answer, now you've got this answer, do something with those two answers. What messes people up is the composition, because if you have this, this means plug 4 into the G function and then take that result and plug into the F function. So this one, you don't do both of them separately and then do something. You actually do it all at once. What you do is you plug the number into one of the functions and you take that result and plug it into the other one. In fact, this is sometimes written like this, everyone. Find G of 4, and then plug that result into F. That's how a composition works, everyone. After you get one of your answers, you take that answer, that new number, which is not necessarily the number you start with, and you plug it into another function. Question?
So, does it matter which one you plug into first?
Absolutely it does, yes. So, note the order I've written them here, plug 4 into the G function, then plug that result in the F function. If it did say this, then plug 4 into F, and then result into G. Absolutely.
So it's the closest one?
It is the closest one, and the way I remember that, that's a very good point. The way I remember that is I just remember that you can write it like this without changing the order, and then it's clear to me that that's the one that gets plugged into first because it's right up against it like that. Yeah, that's great. Check this out. Oops. Plug 4 into F, and then plug result into F again, because it's F composed of F. For the example we're doing right now, since F of X equaled, did I say X squared? Yes, F of X equals X squared. So what this would mean is you would plug 4 into the squared function, you get 16, and you use 16 squared, you get 256. I did that just to show off that I knew what 16 squared was. All right, everyone. We will practice this and learn all the little tricks and nuances we need to know to complete these problems after the break. So I put some notation up here on the board for both combinations, and below you'll see compositions. Like most things, the inherent idea of just plugging a number to two different functions and then doing something with those two different numbers for combinations, or with a composition, plugging a number into a function and taking a result and plugging it into another function, is not the hardest thing to do once you practice it a little bit. Once you practice it, you'll get the hang of it. It's the subtleties that are going to get us. So I just want to talk about these a little bit. Adding two functions together, you might see the notation written like f plus g without an x, f plus g with an x, or f of x plus g of x. They all mean the same thing. And with adding, order does not matter. Because adding things, it doesn't matter if you do, 3 plus 4 is the same as 4 plus 3. It's the same with functions. It doesn't matter if you do f plus g or g plus f. With subtraction, it does. So f minus g is not the same thing as g minus f. Multiplication, order does not matter. The word for that is commutative. An order doesn't make a difference. Multiplication, you do it in any order you want. Division does make a difference. F over g is not the same thing as g over f. So just be aware of that when you are doing these. With functions, that it does make a difference which order you do them in, for some of them and not for others. Compositions absolutely do make a difference. And what I will say is, it is usually the case that order makes a difference. So I will say, just down here at the bottom, almost always, these two are not the same. You can find examples where they are the same thing, but in general, they're not the same thing. The way people say this sometimes, just so you know, is this is read out loud as F composed with G. But you will, however, hear people just say the word fog sometimes. They're saying I'm going to fog these two functions. And this one is pronounced G composed with F, but you will hear people say the word goff occasionally. That they're going to goff two functions together. That's not unheard of.
Would you hear it with like the different letters too, like H and X?
Yeah, like if you had H and P or something like that, you're going to hop them. That'd be pretty cool. Yeah, but usually we just use F and G, so those are the two you hear most often. And the mathematically correct way to say it, if you just want to make sure you just stay on top of it, is say F composed with G or G composed with F. All right, so the things that make this tricky are, there's actually two things. When you simplify after you combine, or compose, and finding domain after you combine or compose. These are the two things that can mess people up when they're either having to simplify them or they have to find the domain. So that's kind of what we're going to focus on today, is because, as I said, in the pre-work you already did a lot of the basics, so we're going to focus on some of these trickier parts to make sure we get that down too. All right, so let's rumble. Let's say that we have f of x equals x squared plus 2x plus 5, and g of x equals x plus 3. Okay, so we have to be careful what they're telling us to do. So if we see f plus g, that one's pretty straightforward. In fact, with f plus g, you don't even need these parentheses that I'm putting in here, but I'm putting them in there just to show you what we're doing. But you actually don't need them because it's getting added. So I will say parentheses not required for this one. And then this would be x squared plus 3x plus 8. I just collect like terms, and I'm done. We'll worry about domain in a moment. Right now we're just going to practice these with functions, because I believe most of the ones you did in the pre-work were with numbers, not with functions. F minus g parentheses required on second function. And the reason for that is if the second function has multiple terms, the minus sign does need to distribute. So if you have this right here, this will simplify to, I'll show both steps in here just so you have it in your notes, minus x minus 3, or x squared plus x plus 2. Remember what simplifying means in these problems? It means clear the parentheses, collect like terms. I'll write that up here. Let me look at clear parentheses, collect like terms. And as we can see, G minus F does give a different result. So you do have to be careful to make sure you do them in the right order. Cool so far? Multiplication doesn't make a difference what order you do it in, but multiplication can be a pain in the neck, especially when you have multiple terms in your equations. So FG, which is the same thing as GF, but we'll just do FG, is x squared plus 2x plus 5 times x plus 3. Now, this is not called foiling, everyone, because foiling is when you have two binomials, two terms in the first parentheses and two terms in the second parentheses. This is multiplying, though, and it doesn't really matter what order you do it in. You just want to make sure you have a system for how you do this. Otherwise, you'll make a mistake and leave something out. Because what happens is this x squared needs to multiply by both of these. But then this 2x also needs to multiply by both of these. And this plus 5 needs to multiply by both of these. So we have 6 multiplications you have to do. And it does not matter what order you do them in, as long as you remember to do all 6. So come up with a system for yourself, like you either do all 3 of these times the first one, and all 3 of them times the second one, or you do this first one here times the second 2 over the next 2 over here. However you do it, make sure you come up with some system for yourself so you don't forget to do one. Once you have your system, you can do it pretty fast. So I did it just the way my arrows said I was going to do it. I did the green arrows, then the blue arrows, then the red arrows. And if you want to, you can check, but you do get the same thing if you do G times F, but it is the same because it's multiplication. Here's the good news, everyone. With division, there is usually no simplifying to do. There's usually not a lot you can do. So F over G, the x squared plus 2x plus 5 over x plus 3, and G over F, the x plus 3 over x squared plus 2x plus 5, and we're done. The reason there's usually not much simplifying to do is because the only way you can simplify is if you can cancel something from the top and the bottom, but you can only do that if every term has it. So, can only cancel if every term on top and bottom has a common factor. And since they don't all have x's, we can't cancel an x, so don't try it. A really good way to mess up these problems is trying to simplify a division one when you can't do it. So actually, we kind of like the division ones. They're one of the fastest ones to do. All right. Now we're going to talk about compositions here in a little bit, but I want to stick with domain, or I want to stick with combinations, which is just adding, subtracting, multiplying, dividing for just a little bit longer. More often than not, you are asked to give the domain of a combination. Hot tip, always find domain before you simplify. That's a very important tip in mathematics, everyone, to always find the domain before you simplify it. I'm going to show you a little mathematical example to show you why that's true. Here's an example of a function, everyone. This is not necessarily a combination or a composition, it's just a function I came up with to illustrate this point about domain. You've all seen functions like this before, and you've probably all canceled an x plus 3 in equations like this before. Has everyone done something like that before? If you haven't, that's okay. The way you would cancel x plus 3 is you would go like this. There's an x plus 3 on top, there's an x plus 3 on the bottom. That means this simplifies to 1 over x plus 5, which is exactly what you should do with this problem. But according to the hot tip above, what should you always do before you simplify? Find the domain. For instance, this one right here, and here's a little throwback to week 1 of this class. You need to jump over the two numbers, -5 and -3, because those numbers will make you divide by 0. Because if you put either a -5 or a -3 in there, you will get 0 on the bottom. And we can't have 0 on the bottom. This is something we learned how to do the first week. First we determined that x couldn't equal -5, x couldn't equal -3, and then we jump over those numbers in the proper order. Simplifying does not change the domain, but can make it so you can't find the domain. This is very sticky, but it's very important, everyone. That's why I need to talk about it, because this is a very difficult concept if you haven't discussed it with someone before. Simplifying does not change the domain, but it does make it so it might be impossible to actually find the domain. Because what happens is, even when you simplify, you must respect the domain of the function in its unsimplified form. So after you simplify this, you might say, well, it looks like the domain is everything except -5. You just can't put a -5 in there. So I'm going to write the domain as this. But that's not correct, because the domain is still what it was before. No matter how you simplify, the original domain is locked and can't change. Class, once you are presented with a function, before you do anything else, you do need to check your domain, because when you simplify it, you might disguise what the actual domain is, but the domain remains the same. If this messed with your head and you're like, what the heck just happened in the last few minutes? Just remember this. If anyone ever asks you for a domain, you must do it before you simplify. That's it. Because this sure looks like I changed the domain, but I didn't. You're actually still not allowed to plug a -3 in here. Why? Because you couldn't plug a -3 into the original function because it would make you divide by 0. 0 over 0 is just as bad as anything else over 0. All right. What do we do before we simplify, everyone? Find the domain. All right. Domains of combinations must exclude all numbers excluded by either original function. If the combination is division, also exclude numbers that cause division by 0 in the new combination. Simply put, everyone, when you combine two functions, you're putting two functions together. Two functions that each already had its own domain coming into it. And you have to make both of them happy. That's what that means. You have to make them both happy. You cannot have something that is not okay with one of the two functions you started with. example. Since f of x can't handle negative numbers, no combination of f of x and g of x can handle negative numbers. Since that original f of x function has a domain that excludes all negative numbers, since this original f of x function has a domain of 0 to infinity, I don't care that this one has a domain of negative infinity to infinity. If I put the two of them together, then I need to make this domain happy. Does everyone see that? Doesn't matter if you add, subtract, multiply, or divide, I need to make sure that both functions are happy. So, if someone asks me to do f plus g, the domain of that is 0 to infinity, because I need to make sure that I make the f function happy. Doesn't matter that the g function can handle anything, since f is a part of this, I need to make that happy. If I do f times g, I need to make that one happy. Make sense to everyone? Let's check this out. If I do f divided by g, suddenly I've introduced a division where there wasn't a division before. So now, I need to make f happy using 0 to infinity, but also x cannot equal 2. Because now there's an x minus 2 on the bottom. X minus 2 didn't hang out on the bottom in its original function, but as soon as I divided them, suddenly it's on the bottom. So now, the domain looks like this.
0 minus.
Got to jump over the 2. Like that. Make the square root happy by not putting anything negative in there. And make the new denominator happy. That wasn't a denominator before, but now is a denominator. So when you divide, you got to make sure that in addition to making the original domains and the original functions happy, you don't divide by 0. This one's tricky. Square root of 0 equals 0. But square root of 0 equaling 0 on the bottom is not okay. So, the domain for this one no longer includes 0. Because yes, I can take the square root of 0, no problem. Square root of 0 is 0. But since now the square root function's on the bottom, can I divide by 0? No. So even though the square root doesn't mind a 0, now since it's on the bottom, 0 is not okay, which is why I've now changed that to a parenthesis, not a bracket.
As close as possible, but never reaches 0.
Yeah, you can get as close as possible. You can put 0.000001 in there, just not 0. Now, before this freaks you out too bad, I want to point out a couple things. First of all, when the functions are different, like a square root and a line, there was not much to simplify. So that's good news, everyone. When the functions were different like this, when I had a square root and an x minus 2, there was really nothing to do to simplify them. There were no like terms to collect, nothing I could really do here to clean this up, nothing I could do on any of these to clean it up. So that's kind of a nice break when you're like saying, look at that, I can't believe there's a square root in this I have to deal with. Well, maybe that's good news because you don't have too much simplifying with a square root. The other thing is this. More often than not, domains are negative infinity to infinity. So, f plus g, f minus g, and f times g will also have domain negative infinity to infinity. And we just need to watch for f over g and g over f. If the original functions have a domain of negative infinity to infinity, then when you multiply them, add them, or subtract them, that's not going to change the domain at all. So if the two original functions have domain, negative infinity to infinity, then what you really have to watch out for is what happens when you divide them. It's pretty slick. Let me show you what I mean. If these both have domain negative infinity to infinities, I can add them, subtract them, multiply them. That's not going to mess with it at all. It's great. But gotta watch out for that division still.
So, we have to, the only time we have to redo our domains is when we are dividing it, right?
Yeah, that's the only thing that will change the domain. You know, you need to respect the two original domains if one of them's not negative infinity to infinity. You always need to respect that, like we did in the first example. But the only time that something new and unexpected is going to happen is when you do the division, yes.
So for the other equations, the answer would be negative infinity to infinity.
All of these, yeah. Domain is negative infinity, and so are all these, negative infinity to
That was the
infinity.
final domain answer, and unless you had a division answer question, then you'd have to change the domain.
Yeah, so let me say it and make sure that we're saying the same thing. If you have f and g that both have domain negative infinity to infinity, you can add, subtract, and multiply all you want, and that will not corrupt the domain. Is that what you were asking?
Yeah.
Yeah, that's it. All right. All right, compositions are a bit harder for domain. When you put one function into another function. It's supposed to be a hollow circle, everyone. That's why we don't use a dot for multiplication, so we don't get that confused. There we go. Compositions are a bit harder for domain, but there is some good news. If f and g both have domain, negative infinity to infinity, then so do f composed with g and g composed with f. If both your original functions have domain, negative infinity to infinity, then you can put one function in the other function, or either way, and you'll still have that domain. So let's practice a little bit with compositions. Check it out. Right off the bat, everyone, right off the bat, I can see that the domain of both of these is negative infinity to infinity. Why? Because there's no division, there's no square roots. Great. That means that before I even do them, both compositions have domain negative infinity to infinity. So that's not a lot to worry about. If they both can handle any number, then you can compose them, and they can still handle any number. Composing is tricky though, everyone. Watch this. You'll be given two functions, and you'll be asked to compose them this way. Maybe f composed with g or g composed with f. What you do, if you're Steve, is you first rewrite it like this, because that makes more sense to me when I see it written like that. That's much more clear to me. I can now see g of x is being put inside f. What that means is I'm going to put x plus 4, because x plus 4 is g of x, into the f function everywhere I see an x, like this. Now we did this in an earlier unit, or an earlier section. We just didn't call them compositions, but we've put an equation into another equation before. What I've done is I replaced both the x in the x squared and the x in the 2x with the x plus 4. Is the computer going to let you get away with this answer? No. What are they going to ask you to do? Simplify, which means clear parentheses, collect like terms. So, x plus 4, a little side, don't never be afraid to do a little side work, everyone. X plus 4 squared is x plus 4 times x plus 4. If you FOIL that, you get x squared plus 8x plus 16. You do not get x squared plus 16. Don't forget the 8x. The squared doesn't distribute, you FOIL. That gives me x squared plus 8x plus 16. That's all I'm going to do on that step because I don't want to mess it up. Now I distribute the 2. Collect like terms. And I'm done. Now, in general, this is a different problem. You will find examples. You will find examples where g composed with f and f composed with g give you the same answer, but not usually. This means that instead of plugging the g function into the f function, we plug the f function into the g function. That's a mouthful. Which means that we are supposed to plug x squared plus 2x minus 3, I think that was it, wasn't it? Yes. X squared plus 2x minus 3 into the g function. Now what was the g function, everyone? What was g of x equal to? X plus 4. So this right here gets put in place of the x in the x plus 4. Recall, g of x equals x plus 4. So, g of x squared plus 2x minus 3 equals x squared plus 2x minus 3 plus 4. You just replace this x with the entire f equation. And simplifying is almost trivial. Almost. Just got to make sure you do it right. Composing is tricky, especially when you have to do all that foiling and stuff like that. They can be tricky problems. Especially when you have minus signs to worry about, they can be tricky problems. And quite often when you are done, you will be asked to find the domain. But the good news is if the domain of your original functions were both negative infinity to infinity, then that's also the domain of your composition. Now, you don't have to love this. I'm not asking you to love this. But does everyone understand what composing means, to plug a function into another function everywhere you see an x? And of course it takes practice with the simplifying and stuff, but you can do it. So what makes this harder? It's harder when the domain is not negative infinity to infinity. Let's take a look at this. Because this is bizarre. We'll start with this one. All right. This has a domain of 0 to infinity, this has a domain of negative infinity to infinity. Now watch this, because this is pretty wild. If someone asks me to do f composed with g, that means that I'm doing f of g of x, or f of x squared plus 1, or the square root of x squared plus 1. You absolutely 100% cannot do this. You want to see your math teacher cry, do this. No, don't do that. You cannot do that, never do that. This is about as simplified as you can get, and I haven't had to do any simplification, but here's what's weird about this, everyone. What kind of numbers can we not take the square roots of? Negatives. What number could you put in here that would make you take the square root of a negative?
Negative x.
No matter what you put in there, it's going to get squared. Does everyone agree with that? Mm-hmm. And what happens when you square a positive number? What do you get? Positive. A positive. What happens when you square a negative number? Positive. You get a positive. This right here has a domain of negative infinity to infinity. The composition is very, very interesting, because what happens is the inside function, in this case, x squared plus 1, gets a hold of a number. X squared plus 1 gets any number first. And since it turns any number positive before we square root, the domain is negative infinity to infinity. So here's what I'm going to tell you, everyone. The easiest trick to remember for determining the domain of a composition is to determine the domain after you've found the composition. But you don't want to simplify anything. This one didn't have anything to simplify, but you cannot simplify first. So we got to be careful. Let's try another one. Here's two functions. What's the domain of the first one? Everything except for what? Zero. What's the domain of the second one? Negative infinity to infinity, x minus 3. You can do that with anything. So if someone gives me these two functions, and they ask me to add them, then the domain is still missing the number 0, because I need to make both parts happy. And so I have to take 0 out because that first part can't handle 0. That's fine. If someone asks me to divide them, it looks like that. Does everyone see how there's two division bars in here? There's this division right here, and there's this division right here. Does everyone see that? What can we never divide by? 0. So we need to make sure that that and that both are not 0. So we need to make sure that x doesn't equal 0, and we need to make sure that x minus 3 doesn't equal 0. Because there's two divisions taking place here, and if either one of those is 0, we're sunk. So we actually have to kick out two numbers. What two numbers do we have to kick out? 0 and positive 3. Well done. So that means the domain is everything but 0 and positive 3. if you enter this into the online homework, it is going to scream at you to do this. How do you simplify something like this? Well, that's a great question. The way I always simplify it is, this is called a complex fraction, everyone. A fraction within a fraction is you multiply both the top and the bottom by the mini denominator. So in this case, watch what I do. Yeah, the mini denominator, that's a technical term. No, it's not. I'll explain to you what I mean by that. Yeah, you see how the numerator is 1 over x, right? That's what's causing the problem. So that means if I multiply the numerator by x, it will cancel that x up there. But that means I must also multiply this by x. So what's 1 over x times x, everyone? 1. And on the bottom, we get x times x minus 3, or x squared minus 3x. The other way people do this is they remember that you have 1 over x divided by x minus 3, and so that's the same thing as 1 over x divided by x minus 3. So that's the same as 1 over x times the reciprocal of that, 1 over x minus 3, like that. The math homework hates complex fractions, fractions within fractions. So whatever technique you've learned to get rid of them, you need to get rid of them. And that's kind of 2 different ways to do it. So we got to be very careful with these domains, but watch this, everyone. Still the same 2 problems. I want to show you something. Still working with f of x equals 1 over x, and g of x equals x minus 3. I want to show you something. F composed with g of x equals f of g of x. Now we're doing a composition. This is f of x minus 3, or 1 over x minus 3. Now I have not simplified anything. I have merely taken this x in the 1 over x and replaced it with x minus 3. Now, you look at this composition, what number or numbers look like they're bad to plug in there? 3. 0 is not bad anymore. Compositions behave very differently than combinations when it comes to domain. The domain of this thing is just missing the number 3, and here's why, everyone. It actually does make sense. When you plug a number into g of x, it will subtract 3 before handing the result to f of x. We need to avoid the number that g of x will turn into 0 before it passes it to f of x. So x cannot equal 3. G of x gets the number first. When you do this composition, g of x gets it first. It's going to take 3 away. And it needs to make sure it doesn't give a 0 to f, so therefore it can't have a 3, because it will do 3 minus 3 and then it will pass a 0 on. Now this is horrible to read. And if you try to memorize this before you take the test, you'll go crazy. So just remember this, with compositions, find the domain before you simplify, but just be aware the domain might change from what you think it might be with the original functions. Because a composition behaves differently than a combination. With a combination, both functions get the number at the same time. With a composition, one equation gets it first, and it has a chance to mess with it before it gives it to the other one. That's why I can change the domain from what you think. So combinations, all parts get the input at the same time. With a composition, one function gets the input before it passes result to the other. This can have unexpected impact on domain. And again, you might be thinking, how can 0 suddenly be okay? It's because compositions work differently. One function gets the number first and messes with it before it passes it on. Combination, they all get it at the same time. So, just be careful. Here's something fun. A few little treats here for the end of the class. Watch this. No. Copy. Here's a table that shows what happens when you plug certain x values into functions. For instance, if I plug an x value in, you find that x value on the top row of the table. So my x value is 7, everyone. You find 7 on the top row of the table. Then you go down to the F row, and you tell me what number you get. So when you go down to the F row, what do you get?
4.
4. If I do G of 2, you find 2 in the top row of the table. Go down to the G row, what do you get? 8. F composed with G of 5. Means the same thing as that. F of G of 5. Everyone find 5 in the top row of the table.
2.
And go down to the G row, what do you get?
2.
2. Everyone with that? 5, 2. That means this is F of 2. Now, find 2 on the top row. You return to the top row with 2, and now go down to the F. What do you get?
0.
Careful. 1.
So that's the answer.
That's the answer, yeah. It's a different way of running a number through a function than running the result through another function. It's a different way of looking at it. And the last thing I'll show you today is this. In my last 90 seconds, this is cool. Yeah. Yeah. I'm just going to show you this real quick. You won't see anything this tricky in the homework, so you don't need to worry about copying this down, but look at this. This right here has a domain of -2 to infinity. And this one right here, you take -x minus 3 and say that has to be greater than or equal to 0. It ends up being x must be less than or equal to -3. So if you were to do the combination f plus g, and you did x plus 2 plus the square root of -x minus 3, this actually can't handle any numbers at all. This function has no domain. You can't put anything in there because you'll make one of the square roots unhappy if you put anything in there. You're not going to see a problem like this. I just thought it was kind of cool to show you how a combination can make it so your domain goes to nothing. I'm out of time, everyone. Thank you for coming. I'll see you all on Thursday.